And if you want to represent it using a simple single equation, it looks like this. It looks complicated, but now that we have dissected it, it's really easy, right? So you score all pairs. You don't even have to do this, right? Because we are doing this all versus all, we have these two matrices. It's actually just a dot product of two vectors, let's say q1 and k1, and that gives me the, the score for q1 asking for k1. But we want to do all of them together, so we use these two matrices. We then stabilize it. We normalize it using softmax, and we retrieve it. We give that soft attention. We instead of doing that hard retrieval, we do this soft retrieval, right? So if we got like a 0.9 for one, it's almost just copying that over, but it can also have, the possibility to take small parts of the other vectors as well. So attention of your KQV is nothing but softmax of QK transpose by DK and multiplied by V. And why under root of D? Why under root of, let's say, 64? Well, this is a hyperparameter. This was a good value. I'm pretty sure if you also hard code it, it will work. But this was, how they came up with the fan-ins and fan-outs. It has that kind of a thinking behind it, right? So just for you to know, if somebody asks, okay, why under root? Why not cube root? Why not, tan h? So that's the reason. And this is like really very important, because now everything is a transformer. Your image, your text, your speech, everything, we talk in tokens. Everything is a token. Token, you have your input, you have somehow created an embedding, and now it's a token. And now we do everything in the token space. I'll later tell you how to do these tokens for images, for words, etc. So there is also a tokenizer in modern LLMs. That tokenizer is learned. But for now, let's just assume we have somehow that embedding. And now after that embedding, that's our token. And now everything is a token. And if you look at code, so we have these these matrices WKQV, which is shared across the entire head, the entire layer. And we then also have the X which is coming in. This is a sequence of tokens. So this is that entire context, because we want to do the matrix operation. We convert it into these KQV matrices. Q basically says what I'm looking for, that Python question. K is basically the badge, what I advertise, and value is what I contain, the final answer that I give. And we then do your QK transpose divided by the square root of the dimension, and then we compute the softmax, and that is my final attention weights or the attention scores. And what I return is the attention weights into the value, right? So this is basically then doing the dot product and giving me the weighted sum of the values is what I'm interested in. And fun fact, it is so important to us that we created our team jacket to say attention is all I need, and it's essentially this attention block which we will learn today, and it has this exact code that I'm showing you here. So it's super simple, and once you do this, what it enables is that you have your word bank, right? So, and this has some embedding. It has, it comes with a vector and has some embedding, right? So this is our X. And now the X dash, right? So the before and after, right? So my my enhanced embedding, my embedding which is after the the transformer layer, right? That embedding, my changed embedding will now depend on my context. For example, if my context had words like river, water and flows, my embedding would look different, right? It will have an understanding of the river and the bank. But if my context had words like money, account and deposit, my enhanced embedding would look very different, right? It would look like it knows about money and bank and finance and so on. So the embedding, the input embedding and the output embedding will be very different based on the context that it appears in. And this is the advantage of the transformer, right? It gives a word meaning, and not just based on my previous thought vector which had to encapsulate all the knowledge from the past. It is based on my current context, and it gets to look at all of them in parallel, right? So this is the big advantage, and this is what we looked at, right? So we looked at the attention head, but we did not look at multi-head attention, and it's very simple, right? Instead of essentially inputting this x into 1, we do this parallelly to many. Why? Because we want to learn multiple heads, where we believe that these multiple heads can learn, let's say, multiple functions. It can learn multiple modes of what that animal word is. It can learn things like grammar. One head can learn action, one head can learn property, because all these heads have their own WK, WQ and WV matrices. So all of them are initialized from random, and now they have the capability to learn all these different concepts such as grammar, action and property based on the need. So we kind of decouple it. It is also good for the GPU, because we can do more things in parallel. And then what are we doing? We are basically, so this is, let's say, our input embedding. It's usually 512 dimensions. It's actually a row vector, and then we give it to all our attention heads. The attention heads now give us, the values, and here our value dimension is 64. So the output value dimension is 64. It's a row vector of 64. We concatenate all those heads. Usually we have 6 heads, and all these 6 heads, 8 heads, and all these 8 heads, we then take those 64 values out, concatenate them into this one long row vector, which then gives us 512, and then we do a fully connected on top of it using a WO matrix. So whatever comes out of concatenation, we multiply it with this WO, and that is what gives us our final output, right? That is what then gives us our final output of that the enhanced embedding, the changed embedding. And this is all that there is in our multi-head attention. So we have our KQVs and so on. So this is part of it. So basically so scaled dot product is nothing but doing that that attention, that self attention, and all of them are doing that self attention in parallel. And then you're also scaled dot product means and attention. They're saying you do your attention, and then you do a scaled dot product of your V's using the output of the attention. You concatenate it, you put it into a linear, and that is what we looked at. So usually you'd have these multiple heads instead of a single head, and this is why they talk about this multi-head attention here. And this is all that there is in attention. So again, attention is really simple. You start with your token, you project it into KQV, the K's and Q's interact and give us scores. We then use these scores to weigh the V's, the payload that it actually carries, and then we then take a weighted sum of these V's based on the scores that have come, and we then have these multiple heads. We take those multiple outputs, concatenate them, use the WO to get the final output of my multi-head attention part. And then after multi-head attention, we do some other things, and we'll talk about each of them in the next video. We'll dissect all of them. We have something called as the positional encoding, etc., etc. So we will look at all of them and then build this entire piece. And as you see, it's really simple if you understand the intuition, if you understand it right.